When I was planning this book, I thought if I wrote a book titled something like Why Einstein is Smarter Than Us and We're a Bunch of Dumb Schmucks, we're not very interested in buying a book like that. But if there's a book about poor Einstein had these terrible problems and we can feel superior and console him, that's really good. You feel, that's a pretty good day. I'm helping my poor little friend Einstein. Everyone's interested in him. I'm assuming most of us here know some of what he did. Just a reminder, aside from minor things, put it this way, the theory of relativity and E equals mc squared was so small, that was just the beginning of his, he was so good he had two theories of relativity. So one in 1905 when he was 26, those of you who are approaching 26 feel anxious. You have like a countdown to getting there. If it's any consolation, you can feel even more anxious if you're younger. There was a fellow I studied with at the University of Chicago when I was young and he was old. And at one point, this fellow was on a boat going from India to England. And he said, oh, it's been so many years that I've been striving and I'm such a failure. I've accomplished nothing. This is awful. His name was Chandrasekhar. The Chandra X-ray satellite is named after him. And he was 19 years old. And in the midst of his despair, he came up with basically the idea of black holes, which was pretty impressive in the 1930s. Anyway, so Einstein at 25 did great stuff, special relativity. At 35, he did greater stuff, general relativity. If Einstein, if he hadn't done special relativity, Poincaré, Lorentz, lots of people would have done it. If he hadn't done general relativity, we would still be waiting for it. Think about that in your field. How many things, if a particular organization disappears, would not get done by anybody else? That's really rare and really special. He was very good. He wasn't just good in science, as you might imagine. He was incredibly good in practical technology. One of his great inventions that he was really proud of and spent a lot of time on in the 1920s was the refrigerator. New improved refrigerators. Refrigerators in Berlin leaked all the time, and he didn't want leaky refrigerators. So he produced a wonderful non-leaky refrigerator. There's a letter to his great friend Max Born, who also a Nobel laureate, and you wonder what Nobel laureates discuss. My refrigerator barely leaks. The new prototype is even better than last time. Next time, down to 3.6% leak. Yes! Einstein was very excited. In 1916, he needed to take a break one weekend, and he was thinking not about refrigerators and not about general relativity, and casually he came up with the key idea behind the laser, which is pretty impressive. The first practical ones, I think masers first, microwaves, were only built 40 years later. This organization would not work very well if there weren't lasers zipping around through fiber optics and stuff. He also came up with the photoelectric effect. If you think about it, there's light, which is kind of energy, and there's electrons, which are a certain substance. And we take for granted, oh yeah, you know, light hitting metals makes things happen. We use it in our phone cameras all the time. How does that possibly happen? How does light, which is energy, how does that make stuff move? It's really impressive. So he came up with that in 1905. That wasn't even his greatest work. Anyways, he was terrific. But then the secret, his greatest mistake, it turned out he made a mistake, a psychological mistake, and it was catastrophic. And it led, even though he was world famous and his mind was still good in his 40s and stuff, and people exactly his age were staying on with good work, he became shunned. He was a laughingstock in the physics community. When he was at Princeton, he was at what outsiders call the Princeton Institute for Advanced Studies. Insiders called it the Princeton Institute for Advanced Salaries. They had a lot of money to bring good refugee scientists over. And for 30 years there, people would say, oh, don't go near him, it's going to destroy your career. Ooh, don't go near him, he's a has-been, he's an archaic nothing. And it really hurt his feelings. Because when he was young and trendy, before the hair thing and stuff, he was on top of the world. Everybody came to him. Einstein once said that people think in two different ways. A quiet quiz, you can see which one is you. He said they're either tennis players or golfers. Tennis players, they just need ideas back and forth. You only clarify it when you talk with other people. Golfers are the ones who, you know, often the neighbors, when they're interviewed by the police, say, he seems such a quiet and nice young man. The golfers are the ones who need to sit quietly and think and cogitate and don't disturb me. They go to find a little corner in a cafe, and with that they come up with great ideas. Well, it turns out Einstein was actually a tennis player. He wasn't a golfer in that respect. And to be isolated from other people, to have nobody come to his office, not have bright grad students want to work with him, that was awful, awful. So it turns out, how did this happen? Why did this terrible thing happen? And there's a curious parallel with high tech. So I'll start talking about how you see this on a large scale, like a sort of a large display, and then we'll zoom back in. We'll take a microscope inside Einstein's brain. So we'll zoom out now a little bit, and I'm going to talk about an organization which many of you will have heard of, and some of you may have studied at, the Cavendish Lab in Cambridge. The Cavendish Lab is about in the early 1900s, the Cavendish Lab was around the size of the floor of this building, a little bit smaller than the floor of this building. It produced, in a 20-year period, more Nobel Prize winners than all of France, all of Japan, all of Italy have ever done combined. And those are countries with terrific educational backgrounds. Think, how could a place about half the size of this floor, maybe with some spill-out labs of the size of this floor, do something like that? That's above and beyond anything else. And it wasn't just patronage. It wasn't that they were rigged on the Nobel Committee. This was stunning work, the foundations of the modern world, modern science. And it turns out there were several things they did. One thing was kind of small. At 6 p.m., they turned off the electricity. You could sit there, but you were in the dark. It means you had to focus. You know, sometimes if you have to give a presentation, it clears your head. If you have to give a presentation with 20 minutes prep, it's not so good. But if you have half a day rather than 3 weeks, you'll really focus in that half day. 6 p.m. electricity was really good. They also helped with visas, very, very useful. But there are two things they did that were even better at the Cavendish Lab. And these later feedback, you'll see them taking place in Einstein's mind. One is that they made their own tools. A long time ago, Air France used to have microphones in the first-class seats from San Francisco to Paris. They thought they would listen in, the French government under Mitterrand, they would listen in on the secrets of Silicon Valley and copy it. Immediately, that's depressing, saying, here's other guys who are terrific. Let's see if we can catch up with them. Much better is to make your own tools and be first, see who catches up with you. There was a young guy working at this Cavendish Lab from Germany, a grad student. He thought, we need a better way to detect little bits of radiation. His name was Hans Geiger, thus the the Geiger counter, named in his honor. They had lots of tools like that. It was this wonderful confidence. That was good. So 6 p.m. stops was good. Making your own tools was good. But the best of all is the guy who ran it was a New Zealand farmer named Rutherford. And he had a concept, what I call a mid-level abstraction. If you tell somebody coming to a research lab, let's be the best, it doesn't really help you. I mean, it applies to Nike shoes. It doesn't give you anything help. If you say to somebody coming to a great research lab, give them some very detailed thing. Philips needs help calibrating this microscope, and we're doing an interesting piece of work there. That's fine. It's great to help Philips, and you can be really good at microscopes, but that's one thing. It's too detailed. What Rutherford did at the Cavendish Lab in the 19-teens and 1920s, come up with what is a mid-level abstraction. He had one guiding principle, which wasn't too abstract and wasn't too particular. He said, everybody who came to the lab, you know what we're going to do? We're going to find out what's inside the atom. Nothing more, nothing less. It's a perfect idea. With that, everybody understands what's going on, everybody can share, but you're not telling them what to do. You give them a real lot of freedom, but they're still pulling together. Saint-Exupéry, the French poet, once said, love isn't looking into each other's eyes. It's looking together in the same direction. If you've ever been in a poisonous organization where people are pulling in different directions, you don't quite understand what's going on. People don't understand why they should work with each other. You'll know how important that was. Mid-level abstraction was wonderful. Second question, so that's how you create a great organization. In this case, the greatest research lab the world has ever seen. Second question, how do they stay that way? And the answer is, they usually don't. They almost always fade within about 20 years. The Cavendish Lab under Rutherford was magnificent. Then after about the mid-1920s, it faded away. That approach didn't work. The outside world was changing. How to find what's inside the atom with tools you can make yourself in Cambridge? It stopped. It was really upsetting. So now occasionally companies can keep on doing the same thing for a real long time. I worked for a while with Shell Scenarios. Shell has a very simple principle. It's not abstract, be the best. It's not incredibly detailed, do this one arrangement with the rock. It's extract oil using really good engineers and make clever political arrangements with the companies that supply it. It's worked well for 120 years. So that's fine. That's a simple, unchanging field. If they can get into clean energy well, I'd be surprised, pleasantly surprised, but surprised. But that's their abstraction. Usually that doesn't work. So Einstein's life, if we go back to him now, he sort of solves the problem about how you can do better than these companies, and he also reveals a possible answer. So like I said, it's going to give a little microscope going inside his brain. So I'll talk a bit about his creativity. And his creativity was very much like those big companies. So the companies, one thing they did was the thing, pulling the plug at 6 p.m. from electricity. Einstein didn't have a limitation with electricity. They often say, you can do mathematics and theoretical physics with just a pencil, paper, and a dustbin, a wastebasket. They also, cynics will say you can do philosophy in exactly the same way, but you don't need the dustbin, which is kind of cruel. Einstein himself loved good philosophers. Kant, at one point, had an image of space-time diagrams, which is really good in the 1770s. Hume's notions about causality and just looking at what you observe rather than trying to understand what's going on inside. These are great, powerful notions. So Einstein, the equivalent of the 6 p.m. stop, he had terrible problems in relationships. His best friend, after his best friend died when they were both old men, Einstein wrote to the best friend's family, Michaela Beso, and said, I admired your dad for being a nice guy and a sounding board, but what I admired best was that he made a relationship with one woman work for his entire life, something which I sadly have failed in twice. So Einstein had spent a lot of time moving from apartment to apartment, flat to flat, escaping from one person, having an affair with the wrong person, going off to another one. It really restricted his time. Sometimes he was writing in trains because he couldn't stay in any city. So he had constraints on his time. For his tools, developing your own tools, he developed what's now kind of standard. He really developed tensors. Those of you who aren't with a technical background, scalars are like numbers and stuff, and vectors are like a number with a direction like an arrow, and tensors just generalize that a little bit more. It's in the appendix to the book. So he developed that, and he especially developed interesting ways of understanding surfaces and stuff. It was his own fresh tools, which meant nobody else had it. Imagine if you have a tool which nobody else has. There was an athlete 40, 50 years ago who was a mid-level jumper. He wasn't incredible, but he found a way, Dick Fosbury, of jumping back. I think it was Dick. Fosbury was his last name, of jumping backwards. This is the famous way that high jumpers jump now. When he had that tool and nobody else did, he was great, even though he wasn't a stunning athlete. Once everybody else had it, he had to fade away. He wasn't that good. Advantages to being first. And then the other great thing that Einstein was good at, his mid-level abstraction. That's a bit technical. I get into it in the book. It was a way of viewing how you can view any physics problem independent of whoever's watching. Whether I'm jumping up and down, whether I'm moving quickly or slowly, how would the world how would things seem if everybody's able to view things and you can't tell who has a special position? It's kind of very much a democracy. I know it's kind of waffly to say it like that, so I have to go leave the details in the book. But he had his unique tools, he had pressures on time, and he had a beautiful mid-level abstraction. He wasn't trying to solve a particular physics problem down here, nor was he saying, I'm going to be the best, I'm going to achieve, I'm going to create greatness. And his abstractions were very, very good. Anyways, it turns out at one point he drew the mechanism of how creativity happens inside his own brain. And those of you who read German as well as I do, which is not too well, will not be following the German. What I'm going to do, while this slides up, I'm going to draw something like that roughly on the board. So what Einstein said is down here are things in the real world, events and stuff that you look at, and then we make a creative jump, a creative leap of the imagination going up here, and from this vantage point we see fresh things. We're up here. Remember, and this is a mid-level thing. It's not incredibly high. It isn't, oh, I'm going to survey the world like a god, but it's not a detailed thing down here. And from here, you draw conclusions. And if the conclusions are right, they match what's down there, and then this jump up has been correct, right? Very simple form. That was his sort of form. And that's what he said, how it works. And from that perch, you can see everything. Anyways, it's a great idea, and Einstein followed it successfully for quite a few years. But then after about 20 years, this happens so often, he stopped following it. I have time to tell you a little bit of the story about how he stopped following it. The book is mostly about that. It turns out in 1915, 1916, 100 years ago, in the middle of wartime Berlin, he came up with an equation that describes the entire shape of the universe. As a rough example, and again, apologies to people who've done physics at a high level, as a very rough image, imagine that space is like a flat trampoline or a rubber sheet. And if I take a little ball bearing and flick it, it'll go in a straight line. And if I flick it in some other way, it'll go in a straight line. Those might be something like planets. You just flick them along. You see the big finger coming down over from south of King's Cross. Okay? If you take a rock or a heavier ball and put it in the middle of that sheet, it'll sag down in that sheet, right? And think of that as like the sun or something. Then if I flick a ball bearing, the ball bearing, instead of going straight, well, it will if it's far away. If the sheet's sagging down here, the ball bearing will veer around it like in a billiards or pool table and stuff. kind of makes sense. Again, it's only a metaphor. Here it's curving in space. In fact, in reality, it's curving in space-time. It's a wonderful notion. Force then becomes just a distortion of space. The geometry leads you along. An example there is two people walking to the North Pole. You can start at different points on the equator, and you look at each other, you're a few yards apart, and you say, we're going to stay parallel, we're each going to go due north. But you realize that the geometry will force you together. You'll see this person coming closer and closer to you, say, oi, you're not going straight. He'll say, the heck I am, I'm going perfectly straight. So an ineluctable, what appears to be a force, can come from distortions of geometry. That's a two-dimensional surface in our three-dimensional space. Space-time is four-dimensional, so that's how it works. Anyways, the details are in the book. That isn't what matters. What matters is Einstein came out of it with a beautiful equation, G equals T. Very roughly, geometry creates how things move, and the structure and shape of things, which includes mass and energy, will shape the geometry around it. The fact of a heavy bowling ball will sag the sheet of space-time around it, and the curvature of space-time will show that there's got to be something there, something there behind it. What a beautiful idea. Among other things Einstein worked out shortly afterwards in 1917 was that this predicted that the universe was expanding. What an amazing idea. And he went to his astronomer friends and said, I've predicted the universe is expanding. These two simple equations that seem to reveal the truths of the universe, explain the universe is expanding. And his astronomer friends in 1917 said, big mistake. The data shows the opposite. The universe is static. The Milky Way galaxy is just sitting here kind of floating, and beyond it is a void. Sort of like looking into Donald Trump's mind. There's just nothing there. Maybe some malicious entities and a little bit of sneering coming back at us. That's it. So Einstein had to put in a modification to his equation, the famous lambda term. And instead of this beautiful symmetry where he thought not so much that he detected the hand of God, he wasn't an atheist, he wasn't a formal religious believer. He was anti-atheist. He said, how could you be so sure? He was sort of in between, kind of like Spinoza, if you're interested in pantheism. It's quite extraordinary. There are these subtle structures there. He didn't know why or what they came from. He once gave an image of humans as being like a little boy in a big library, in a dark, it's at night, it's maybe foggy out, and the walls of the library, there's all these bookshelves around with books, and in those books are the secrets of the universe. They actually exist. They've been specified really clearly. Very occasionally, the brightest members of our species can walk forward, go up to one of the books, open it, and you'll actually see it. One line might say E equals mc squared. Wow. Another might have the tensors behind G equals T. But then we usually have to close it, go back, and retreat. But we know it's there waiting. Einstein loved that. Newton had seen some things. Einstein was lucky enough to see some things. Future generations could also. It's a wonderful Platonic dream. Anyway, so he felt bad that he had to modify that simple G equals T, but he said, okay, if the data doesn't show that it's correct, I'll have to modify it. So he made his equation ugly for 10 years. 10 years later, Hubble in California and other people said, oi, did we get it wrong? Oi, did we get it wrong? I'm adding the oi. They probably didn't say oi. And they said the universe is expanding. They found this wonderful evidence that, boom, it's expanding, and each part is expanding from the other parts at a terrific rate. And Einstein was so happy at that. He said, I knew it. I knew it all along. Have you ever, any of you here seen Galaxy Quest, the film? Remember there's this a teenage boy on Earth who believes that aliens are speaking to him and stuff. And nobody believes him and stuff. He says, oh yeah, I know, it's just made up. And then he actually sees them this way. He said, I knew it. I knew all along. It was actually true. So that was Einstein after 10 years. He realized he had to stick to his original, he should have stuck to his original thing. The experimental evidence was agreed on by all the astronomers in the world, but they were wrong. If he had just held his nerve a bit longer, he would have been proven right. How cool is that? Two simple forms, two simple tensors, G equals T. Again, I'm summarizing, but basically that somebody came up with in their head in Berlin during World War I, predicted that, that our local cluster is expanding away from other parts of the galaxy. How utterly extraordinary that advanced primates can do something like that. It was wonderful. Anyways, what conclusion did, so let me see. So what Einstein did here, so he came up here. So one of his principles there would be, say, G equals T. And the things he found there, it showed that the universe was expanding. So I'll do like that. It showed the universe was expanding. It also famously described, it explained how Mercury wobbled as it went around the sun. Mercury's orbit wasn't quite what you would think. The curve down there by the sun, the decay of that trampoline or rubber sheet was greater than Newton would have predicted. Mercury, I believe, is that. So that was under there. And he had all sorts of predictions, and they really held up. It was when and that was the simple G equals T. Anyway, so all that's good. You think, okay, The technical mistake, he gave in, he shouldn't have given in. It's sort of like they often say in business, reinforce victory, starve defeat. But of course, when is victory? You release a new product, it's not doing that well, maybe market penetration is slightly. Give it a little bit longer, it's really good. A bit more ads, a bit more improvements and tweaks, we have it. At what point do you stop? Einstein thought that he had stopped too soon. Anyways, from this, he drew a catastrophic conclusion. He decided that one never had to listen to experimental evidence if you believe that something clear and simple had been found, right? That those instructions that the divinity or the divine forces or just the facts of the universe had made, he was kind of ambiguous on it, that had to be super clear. Those things you found in the books in the library, they had to be really, really simple. Quantum mechanics started coming in around this time. And Einstein had helped create quantum mechanics in 1905, but in the late 1920s, it was getting even better. The famous Heisenberg uncertainty principle, things like that. Einstein thought, oh, well, this is all very interesting. The mathematics is really good, and it's a temporary epiphenomena. Our equipment can't tell exactly what's going on, and of course, probability is very useful. His early work on the lasers was exactly with probabilities of electron transitions. He said, that's fine. Heisenberg at one point was so excited by Einstein, he visited him in Berlin and said, Professor Einstein, I loved the way you just used observational evidence without trying to wonder what was happening backstage when you came up with relativity. That's what I did in quantum mechanics. Thank you. Einstein looked at him. It's not what I meant at all, he said. I didn't mean anything like that. He thought that it was just provisional if you didn't know the details. Eventually, the details would be clear and exact. So Einstein couldn't accept quantum mechanics. And as evidence came in and there became more and more evidence, he wouldn't accept it. Now, it turns out he couldn't do it. Some individuals, so he was stuck up here. This had worked really, really well. Boom, applying for this, applying for that. Why should you ever change it? This is wonderful. There's something here that it didn't apply to. Well, that was temporary. Remember, he had been burned once with the expansion of the universe. Maybe he would, again, imagine you're pushing a product and you pull back on it too soon. A competitor does it, and it works perfectly well. He says, I knew it. I should have just waited. I have to ignore everybody's comments against it and stuff. There's times to really stick to your guns. Same thing in math, same thing in physics. You're working on a certain approach. You don't get the right answer right away. Oh, I'm nervous. I have to jump back. No, sometimes you have to stick. The question is how long? How long? Some people think that, well, Einstein faded in his 40s because in your 40s your brain, isn't as nimble as it was at other times. Those of us, or those of you who are anxious about not being up to the Chandra level at 19 or Einstein at 26, can remember if you're really, really quick at mental arithmetic, that tends to peak just before age 11. And if you're good at picking up languages, to get a perfect accent is almost impossible after the late teens, early 20s. Something changes in the brain. You can become fluent, very fluent in language, but the perfect accent just gets harder. So the question is physics like that? And the answer, curiously, is no. Chandrasekhar, that person that I mentioned, one day, and I think in the early 1980s, his wife elbowed him in the ribs in Chicago. She told me this later. And she said, Chandra, wake up. It's a Swedish Academy. You have the Nobel Prize. And he said, without any arrogance, he said, oh, for which discovery? He had about 6 or 7 that were worthy of the Nobel. And he was doing great work into his 60s, even into his 70s. Raleigh in the 1800s did that. So there's a number of people who do it. And in particular, Einstein's best friend for a while was Niels Bohr. Niels Bohr, the great Danish astronomer, who apparently, physicist, who apparently had one language, which was called Bad English. He could speak Bad English with every accent. He could speak it with a Danish accent. He could speak with a French accent. Wherever he went, people found it. I can't quite get what you say, like that. He would mumble. He was a wonderful man. And in his 60s, even in his 70s, at his institute in Copenhagen, bright young grad students from around the world wanted to work with him. Einstein's famous for saying, God does not play dice with the universe. God does not play dice with the universe. Niels Bohr said to him, once Niels Bohr had accepted the evidence from quantum mechanics, once Niels Bohr had looked down at these new things, these quantum results, Niels Bohr said to him, Einstein, stop telling God what to do. Looking at the universe, stop telling him. So Niels Bohr had actually moved over here. This is G equals T, but more importantly, it's the notion that everything should be exact. I'll call that a little right angle. Everything should be exact. Niels Bohr went over here, and he had a slightly different abstract principle, which accepted the principles behind quantum mechanics, that there's going to be a certain fundamental probability. And as far as you go down to the universe, it isn't exact. There's going to be probability and uncertainty. It isn't terrible. Things are cusped and limited, so things as they come to the macro level are fine. We can make transistors work very, very well, but within transistors, these quantum effects are taking place. That's what happens. So Niels Bohr had actually managed to move over here, and from here he come with various clues. So imagine this is something that doesn't apply there, but in Niels Bohr's thing, it applies very, very well. So he was able to move there. Einstein couldn't. The Cavendish Lab, remember I told you the Cavendish Lab fell apart. For 20 years, find out what's inside the atom was a perfect guiding light. It's the sort of thing, if you've ever been watching a video at home and somebody comes in and says, oh, what's going on? You give them a little, you whisper something, or if it's 24, you're saying, Jack Bauer's almost about to get the person, and the rug's going to be pulled out from under him, and he'll have to get the person a different way. That can apply to any 24 episode ever. But often you go into a movie, and people will whisper what's going on. The great thing about these mid-level abstractions is you can whisper to somebody, and they get all the knowledge of the people who've already done the hard work. How cool is that? I can whisper to you the rules of calculus. You're smarter than Newton. I can whisper, even in a simple book like this, a bit of general relativity. You're past what Albert Einstein himself did in his 30s. It's really awesome. The Cavendish Lab, they whisper to people who are really bright in physics, let's look what's inside the atom. And immediately they have a good research proposal. Einstein, yes, so that's what they did. But it faded after a while. And then about 15 years later, somebody else took over the Cavendish and said, you know what would be a really good mid-level abstraction? Let's use X-rays to study crystals. How about crystals of proteins? Yeah, let's use X-rays to study protein crystals. That was fabulous. That's how DNA was discovered, right? It crystallizes beautifully in the X-ray diffractions. You can work backwards to find the double helix structure. Hemoglobin, it was magnificent. And they started out, boom, with another burst of Nobel Prizes, one after another, for about 20 years. What happened next, you'll have to read elsewhere. So one can do it. So anyway, so I said we would give the examples of science and then go back to business, about which I'm profoundly not an expert. Thus, we can have a discussion on that, or later we can have a discussion about the curios about Einstein. You can ask me about his blue parakeet, but I won't tell you about that now. So this diagram, which Einstein was so proud of, and I show you the picture of, suppose you change it a little bit. So down here, instead of like the expanding universe, which is noticed, or Mercury, which is noticed, you have things like something like there's a big internet, right? And then you go up to there and say, what's going to be a really good way to deal with a big internet? There were companies like Yahoo and stuff that dealt with, I don't know, they dealt with it in one way. What if you have the notion up here, not G equals T, you're not doing tensors and general relativity, but you say, I know a really good search system, plus maybe ads to monetize it. That's going to be a good way to deal with it. So these things down here, a big internet, wow, it applies to it really well. And there's all sorts of other things that applies to it really, really well. Certain companies come to mind that were very, very good at that. So isn't that neat? So that same logical form, there's data down there, there's stuff in the real world. You make a jump of abstraction, which isn't going to come from anybody telling you. You have to be exceptional, like Rutherford at the Cavendish Lab, like Einstein in 1916, to come up to it. And once you're up into it, also ordinary people, ordinary skilled people, you put them in that chair and they can do good stuff. Captain Kirk is sitting inside a wonderful chair. He could not create the Starship Enterprise. Any of us sitting in that chair, including Justin Long from a Galaxy Quest, will be able to press buttons and shoot phasers and just do all sorts of cool stuff. If you're in the right perch and position, you have magnificent power, right? People can come into a company like this, and when this matches that, they don't have to be the terrific entrepreneurs or geniuses who come up with this. They just walk right in there. Now, Niels Bohr was able to walk across from this to that. He was a very flexible man. The thing is, not everybody does. So what happens, so this worked really well. So will a company like this, and again, this is purely speculative, will a company like this last forever? Well, there's lots of new stuff coming on down here. So apps can be sometimes hard to search. They can be like a walled garden. There's concerns with privacy. There's all sorts of stuff like that going on. There's notions of how do you discover things that haven't already been categorized in some way. Just lots of new stuff. And then there's even stranger things happening. When this company here was formed, hipsters in Shoreditch didn't exist. Shoreditch was a terrible slum. Brooklyn was a place where people went if they got divorced and didn't have any money. So there's people with a slightly different culture. Maybe people who don't like to own cars. It's no longer cool to own cars. It isn't part of your definition. A better definition could be, I don't know, having real life experiences, live music or genuine fitness or triathlon, something like that. So new categories are coming up. Apps, blah, blah, blah. Very occasionally, people from here can change themselves, but it usually doesn't work. Remember, the Cavendish Lab had to jump over to a different view. They couldn't modify looking what's inside the atom to going there. They had to have new people came in. Rutherford died. Max Planck, the great physicist, once said, you never out-argue your opponents. You outlive them. And that's something. So it went over there. Occasionally, a person can make that move across and move sideways. So think of, again, to the extent, if search is going to have limits with some of these other things over here, new data bits down here, suppose you have something else, alphabet, lots of things over here, quite different. So there's a big structure like that. And then from there, you can maybe apply to these things better. You can apply to those, and maybe, who knows, fresh things will come up. We don't know. Now, the question is, who fills those slots? Who fill those slots? Einstein went to one slot up here, and he could not move across. Niels Bohr said, come on, it's different from what you've learned, come on. Yes, you were really bright at university doing this. Yes, you were terrific coming up with these tools and these tensors. Come over here and use this new stuff. You will come up with great things. And the sadness, the pathos, is that Einstein's mind was up to it. As an older man, he said, one implication of this quantum mechanics, if it were to be true, is quantum entanglement. Oh, that's almost impossible. His mathematics was exactly right. This is 1935. Almost a century, actually a century after that, I think we'll have quite nice quantum computers, a bit specialized but doing well. He came up with gravitational lensing. All of this is as an old man. His brain was terrific, but he just ventured there briefly and would go right back. Oh, I got to do it this old way. So very rarely can one move across. Sometimes you have to acquire brand new people. That's why many companies do well. They have entire new groups, either spun off or brought in or something. Occasionally, however, magnificent people like Bohr can go up and work across themselves and step by step into these different things, which will have those fresh implications. So I leave you with the question, are we Niels Bohr or are we Albert Einstein? And after reading this book, you'll think, gosh, I used to think Einstein was terrific, but now I don't want to be like him at all. Thank you.
Thank you very much. We have time for questions, so please wait for the microphone.
So Einstein created Schrodinger's cat, didn't he?
Yes.
So that was basically saying quantum physics is ridiculous, right?
I don't want to ask hands up of people who don't know about Schrodinger's cat, so I'll give a background. One conclusion I would say is that if a man named Schrodinger, if you were transformed into a cat, like you stepped out of the internet and, oh, I'm a cat and stuff, and there's these strange people around, and a man named Schrodinger comes up to you smiling and says, would you like to come home with me? The answer is no, under no circumstances. It's not a good idea. Schrodinger was a man that Einstein really loved because of his personal life. Schrodinger's wife used to reward him when he had great results. She would introduce him to really nice twins to go off to the mountain with and stuff. They said about Schrodinger when he came to Oxford in the 1930s, to arrive at Oxford with one wife is bad enough. To arrive with two, really excessive. So Schrodinger had this wild sort of bohemian life, which Einstein liked. That's one reason Einstein grew his hair like that. When he was young, he was actually kind of dishy. He was a good-looking guy. When he was rowing, people said, oh, you're really, really muscly and stuff, when he would sail and row and stuff. But later in bourgeois Berlin in the 1920s, he wanted to fight that, to say, oh, you don't have to line up and be exactly like that. His second wife was incredibly particular. Albert, I don't think that's quite the right way to hold our forks, that sort of thing. So he did the hair as a sort of resistance. So he liked Schrodinger, and the two men were really good friends. And they collaborated in the mid-1930s by letter. Schrodinger had gotten a job in Dublin, of all places. It turns out the guy who ran Ireland at the time, De Valera, had studied mathematics. So he respected Schrodinger. And in their correspondence, they came up with this notion. It turns out very often people come up with a notion to disprove a theory, and that notion is really good. And the reason is we don't like humiliation, we don't like fear. A friend of mine was a very successful TV and film writer and producer, and he was really good. Then when he got a lot of money, he sort of lost his creativity. And he tried all sorts of ways to get his creativity back. He tried working with bright young people, going to museums, working in different fields. None of it worked. And then his business partner ripped him off. And boy, was he motivated. He started writing terrific stuff. So Einstein still disliked the fact that he'd been pushed to the side. So that brought up his creativity to a real high level. You know, if you're fired from a company, you want to show them. You're full of energy, you have to show them. So he came up with, in correspondence with Schrodinger, Schrodinger was involved a little bit, with this notion of Heisenberg's cat, that if there's no way whatsoever to predict if a certain particle is going to decay this way or decay that way, then the following curious effect happens. And suppose you can't predict which way it's going to go, and you will only know, will you only know, or will it only happen once you look at it? Suppose that particle's inside a box. Suppose the poor cat is inside the box. Suppose a large gun. You see the viciousness of quiet, often vegetarian physicists. They should the gun have impaling hooks? Should there be a little trap door underneath it and stuff? And suppose if the particle decays and goes this way, nothing happens, the cat walks around, da-da-da-da-da-da. If the particle decays and goes that way, a big gun blasts it to smithereens, right? In a standard interpretation of quantum mechanics, you not only know until you open the box which way the particles decayed, it hasn't happened. It's ambiguous until you open it and look, that the actual observation helps create it. Einstein thought that was insane, but yet a lot of evidence, again, I'm being metaphorical about it, a lot of evidence backed it up. The question, of course, is Einstein said, well, in that case, is the cat alive or dead before you open the box, right? We don't know which way the particle went and if the trigger was pulled or not. So is the cat alive or dead? And clearly it can't be in a superposition of two states, half dead and half alive. On the other hand, if any of you have ever taken the Northern Line in London at about 8 a.m., you understand many people can be in that superposition of two states, half dead and half alive. So that was a short, and they came up with that notion to sort of disprove quantum mechanics. And people like Niels Bohr and other bright young people working with him thought, good point, yep. There's a superposition of states until the observation takes place, and that has certain consequences, and lo and behold, those consequences were used by John Bardeen, who was working at Princeton at the time, to develop a transistor. It's actually true. How curious is that? Einstein wouldn't step sideways to accept it because he had been so comfortable in that previous position. I have a little addendum to the answer, but I'm going to stop giving really long answers. If there's time, I'll give. Just remind me about the playing card problem. But I'd like to have some more questions first.
Next questions? Any questions?
Yeah.
How much of his reluctance to accept new models do you think stem from a strong sense of aesthetics and beauty? The two tensor equation.
Yeah.
And the offset concept. How much of that was just like, oh, it's too ugly, it's not pretty, I refuse to accept it.
So the question is, how much of it was maybe not necessarily religious, but it just came from simple aesthetics, beauty rather than ugliness and crudeness? The answer is a real lot. The two possibilities are related. Einstein believed in the need for architectural simplicity a little bit because of his religious views. Einstein was once interviewed what he felt about music. And he was like the guy, the boss you can never please. People said, Mendelssohn, what do you think about Mendelssohn? Oh, Mendelssohn is wonderful, the beautiful lyric tunes, but he lacks a certain architectural whole. What about Schumann? Oh, Schumann, I really feel for Schumann, but it's not incredibly pure and great. What about Beethoven? Now Beethoven is terrific. It's emotional, it's powerful, but it's a little bit arbitrary. Aren't those emotions arbitrary? The one he loved wasn't even Bach. He loved Mozart. Because Mozart is not just the surprise. The thing with Mozart is what comes next is unexpected but plausible. How cool is that? Unexpected but plausible. That's what's happening. It's like a really, really good thriller. But often it felt true. It wasn't just a little game. It felt, you feel that a little barrier has been removed and you're seeing truths of the universe and bits of Mozart, at least for Einstein, and sometimes for me. Can I just say as a footnote, Mozart's clarinet concerto, I once listened to when I was in the south of France and had 2 recordings for about a week. I can never hear that again in my life. People tell me it's beautiful, but please don't play it in my presence. But as for the aesthetics, that would be it. And when Einstein was dissatisfied and unhappy, when he was young, he played the violin, and he played really well. But when he was older, his fingers got a little bit arthritic. And what he loved was just noodling away on the piano. He would noodle for hours and hours and hours. In Berlin and Princeton, a little bit of jazz, a little bit of classical jazz, all sorts of stuff. Aesthetics meant everything to him because he felt they were a sign of something very, very true. And it drove him into isolation. How sad is that? Next.
Questions?
So, out of all of Einstein's mistakes, which one would you say would be, if you could pick one, would be his greatest mistake, which would have prevented him from contributing more than he already sort of has?
Great question. So out of all the mistakes, what was the key? What was the worst, the most fundamental mistake? And many people think the mistake was modifying the G equals T equation. Again, that's just a metaphor. Modifying it and adding extra terms. But that was a mistake, but it's a mistake that anybody can make and then fix it. Oh, I see, I was wrong. And you go back with the same attitude that he'd had when he was young, that you would climb up here, which is beautiful, but then you would check things against the consequences. And if ugly facts really got in the way, you would have to change this, however beautiful it was going up. So I think his mistake wasn't the scientific mistake about the lambda, the extra term. Anybody could have done that. The mistake was diving in and saying, it was a psychological mistake. I've been burned once, I'm never going to be burned again, right? Tony Blair had a possibility early in his tenure as prime minister to help NATO forces go into Kosovo. And a lot of people said, don't do that. It's imperialism, it's not going to work, it's really messy on the ground. He ignored them, he went into Kosovo, and on the whole it worked quite well. A few years later, he wanted to go into Iraq. People said, don't go into Iraq. You're going to mess things up. It's a hornet's nest. Everything will get worse. And he said, they said that before, and I was right. I stuck to my guns. I'm going to stick to my guns again. And in fact, he was wrong the second time. So that was Einstein's problem, that second mistake. Now, it happens a lot to people who are at the top level because they were so successful before. If I have like a plausible hypothesis and then it's proven wrong and then it's later proven right, that's nice, but it's just a plausible hypothesis. But if I come up with general relativity, wow, and that's finally, proven right again, I'm really not cocky, but I'm very confident in my beliefs. I feel, even if I don't feel I'm speaking for myself, I feel I've been able to find something true about the universe. The people who hustle really, really hard to get to the top usually have one shtick, one special approach that really, really works. And they have to push hard to get it. And it's often a magical approach. It almost never happens twice. Lester Thurow, the guy at MIT, who cruelly has been described as less than thorough, which is mean, pointed out that hardly anybody who creates a company creates two different companies, ever. Occasionally there's people who do it. That idea, unfortunately, came to me as a teenager. I read his book, and it bothered me so much that the first time I had a bestseller, I thought, yeah, well, but I had a second one 10 years later, and I said, yes, Lester, yes, we can do it. We can do a separate thing. First time could be luck, second time, okay, one knows how to do this stuff.
So I have a question. I want to know what fascinates you so much in Einstein specifically that you not only write a whole book about him, but wrote a second book about him.
I'm amazed at what human beings could do, and also ordinary human beings. I grew up in an ordinary Jewish family in Chicago after World War II, and many people in the neighborhood would have a picture of Einstein up on a refrigerator or an encyclopedia about, and there's a thing of Einstein, and I thought, this is a noble and good man. I feel some connection with him, but I had no idea what he did. I had no idea. Some people, I don't know, they invent a computer or they invent a car or a particular device or an airplane. It's beautiful, but when I was a little child, I didn't know what Einstein had done. At university, I learned about it, and I was amazed. It was sort of like listening to Mozart for the first time, or in my case, Mozart, especially the clarinet concerto, but like good blues or something. You listen to it and it feels, this is really true. Sort of like on a really good date. On a mediocre date, you tell your cute stories, they tell their cute stories, but on a really good date, you're just connected. You're just directly connected. There's no artifice from top to bottom and stuff. So when I was learning about Einstein, I thought, wow, he cut through in the universe. He saw what's really there. This notion of geometry inducing the sensation of force, as with people going to the North Pole and feeling they're pulled together, or with gravity coming that way, that's incredible. So I really wanted to share it. And then I wanted to find out, how did he do it? I mean, what sort of man was he? What was his background? One thing that helps in a background like that is to be not a total outsider. If you're a total outsider, you don't have enough education, but not to be a total insider either. It helps to be sort of on the edge. Moderate discrimination works really, really well in science and in business, very much. Total discrimination, they don't give you a chance. Moderate discrimination, you know two things. A, you have to work a little bit harder, and B, what you learned before about the system isn't necessarily true. Suppose somebody grows up say in an extremely religious, say fundamentalist religious view. As a kid, they're taught, say, that the world is based on turtles and it's turtles all the way down. They go to university and the people there who teach astronomy say, that's nonsense, it's not like that at all. Here, I'm going to teach you the latest results, this is what we know is totally true. The person might think, Maybe, but maybe not. What my mother taught me was wrong. Maybe what I learned from you, maybe that, not necessarily as wrong as that previous thing, but I'll be a little bit cynical. Compare that to somebody who was, say, a professor's kid. They grew up learning the latest results, on a simplified version, these nice books you buy for your kids when you feel guilty and you're watching Jack Bauer save the day again. And then when they go to university and it's more of the same. They have no reason to be really, really critical. So Einstein was enough of an outsider to be critical, but not so much that he was that he had no training.
Time for more questions.
So how did he hold on to his skepticism about quantum theory when, I'm assuming there were experimental results, like experiments backing it up?
Yeah. So how did he hold on to his skepticism? I suppose he held up to it, well, a couple of reasons. One, he had seen that large groups of people can be wrong. All the astronomers in the world, everybody, whether they were very theoretical or very practical, they all were persuaded that the universe was static for 10 years or 8 years and stuff. And it's like, ooh, they had been wrong. They had been wrong once. What if they had been wrong for 20 or 30 years? There were certain results. The ability to measure things in the universe was very difficult. To measure absolute distances is hard. We know that if we know the absolute brightness of a car headlight at a certain distance, what we perceive of it is going to be high or low, and then the intensity, and then we can work out from its absolute magnitude how far away it is. So it took a long time until astronomers, there was a woman named Henrietta Leavitt in Boston who managed to find a way of measuring the distance to nearest galaxies, and that allowed us to get a proper yardstick for the universe. So suppose Henrietta Leavitt hadn't done that. 50 years may have passed. Einstein knew he was lucky, it only was 10 years. So it could have been past his death, past his whole lifetime, that people thought the universe was static, and lo and behold, it was not static. The greatest authorities. So that was one. The other thing is, in the 1920s and 30s, he saw entire countries go mad. Just countries go mad and nuts. In 1933, many books were burned in Germany in public, including in the greatest university town everywhere in the world then. It was Göttingen. It'd be like, could you imagine if at Cambridge and MIT and all those places, they start burning books with enthusiasm from the students. And Einstein's books were some of those that were burned. It was non-Aryan physics. It was terrible. So he knew, hey, entire organizations can go nuts. I just have to be quiet and wait it out. But he was wrong.
Anyone else? There are no more questions, then I think we can finish here. Thanks again, David Bodanis.
Thank you.